Okay, so what are the things that we can say about this model? First of all, what are some of the properties? Well, we can calculate what the expectation of y is. And I should say we can think of this. So right now, during this calculation, I'm making the assumption, just for my convenience, that the x's are non-stochastic. And so I haven't said that the expectation of y is conditional on x. But we can think of this as basically the conditional distribution of y given x. And so basically, if I'm assuming that the x's are non-stochastic, it makes my life a little bit easier because I take the expectation of beta naught plus beta 1 x sub I plus epsilon sub I, and the x's are non-stochastic, so they're just constants. They come outside the expectation, and it just sort of makes the calculations easy. Okay, and so we get, in particular, that the expectation of y sub I is equal to beta naught plus beta 1 x sub I. Okay, we can do a similar calculation with variance of y sub I. And we get that that is just equal to sigma squared. So it's the same variance as the error. And then we can also do a similar calculation showing that for any I and j, where I is not equal to j, the covariance between y sub I and y sub j is equal to 0. Okay? Yeah. Oh, and so I just want to emphasize the betas then are parameters in the conditional mean function. Okay, so we've got this linear function. We've got sort of a set of assumptions that we're willing to impose for now. So our next question is, how do we find estimates for beta naught and beta 1? Well, I'm just going to throw up 3 different options, and I'll very quickly dismiss 2 of them. But just so you know that there are sort of other things that you can consider other than least squares estimates. So one thing that we could do is we could find the least squares estimates. In other words, the values of beta naught hat and beta 1 hat such that this expression here is minimized. Okay? And I'll show you pictures of what these look like in a second. We could, instead of minimizing the sum of squared errors, which is what, so each one of these in this parenthesis is a well, if it's an error if beta naught and beta 1 are the true parameters, it's a residual if they're the estimates. But what we do is, if we plug in the estimates, we call that a residual. And then if we square the residuals and sum them up and find the parameters that minimize that sum of squares, that's called a least squares estimator. Instead of squaring them, we could just take their absolute values instead and come up with something called the least absolute deviations estimator. That's the second possibility. Or a third possibility I'll throw out is something called the reverse least squares estimator. Okay? Let me just show you pictures of each of these in turn. So actually the least squares estimator and the least absolute deviations estimator have the same picture, because what we're doing is for the least squares estimators, we're just taking this quantity here and squaring it. And for the least absolute deviations, we're not squaring it. We're just taking the absolute value. Okay? So they have the same pictures, but what we do is for the least squares estimator, we compute all of these deviations, and we choose the line that minimizes those squared deviations. So these are the first 2 possibilities, and then the picture for the third possibility just looks like this. We're minimizing the sum of squares of those deviations instead in a reverse least squares estimator.